Welcome to Applied Business Analytics. This is a short video on neural networks. There are many videos on YouTube on neural networks and many things you can read about neural networks. This is a very simplistic introduction to neural networks. And neural networks have been around for quite a while. They've now got the new monikers such as deep learning, but this is an actual website from the late 1980s, early 1990s, because the idea was, oh, this new technology can be used, of course, to pick stocks and make money. And the idea of the neural network was a big brain here and it had all these inputs. And the idea to have an output that either say buy or sell. And that's the idea. Is the idea, can we mimic the human brain and somehow make decisions like the human brain makes decisions? And the neural network was an idea of how to model the human brain, of course, using algorithms and softwares. There were connectionist machines in the 1980s. There was the idea of building special chips that were neural network chips. And the idea took off and then it stopped for a while. It's becoming very, very popular. But what we're going to show in this video is just a small introduction to the ideas behind neural networks. Essentially, neural networks take inputs, does ideally something intelligent, and then gives you an output. And that's what's going on. You're not going to get a model you can really show someone or you can really write down on paper and understand what's happening. You can't say the effect of X3 has this kind of effect on Y. So it doesn't give you as nice a output model as linear regression or logistic regression in terms of interpretability. But again, if the name of the game is prediction, if you're trying to get the best predictions possible, neural networks is a tool you should have available in your toolbox. How does it work? Well, basically, it's building something similar to synapses in the brain, where you have what are called input nodes. You have an output node here. Then you have hidden nodes, middle nodes. And there can be several layers of hidden nodes, and there can be 1, 2, 3, a whole bunch of hidden nodes. There's the Bolzano-Weierstrass theorem. Of course, you're all familiar with that from high school. Maybe if you went to high school in Russia. But essentially, any continuous function can be approximated to any degree of accuracy by a sum of polynomials. And the same idea sort of holds for neural networks. With enough hidden nodes, you can approximate really any continuous function you want under the sun. Now, it's a existence theorem. It doesn't show you how to do it. It doesn't tell you how many hidden nodes you need, but it says this is not a horrible idea to do. You could approximate whatever you want to do with enough hidden nodes. And that's what the neural networks are doing. It's just a complex way of essentially modeling a y as a function of x's. So simplified mechanics, where we have inputs, sorry, actually an x2 over here, and h1 is going to be a function of x1 and x2. h2 is a function of x1 and x2, usually a logistic function. So what we mean by that is g of x equals e to the x over 1 plus e to the x. And then y, it's your predictions, it's going to be a combination of h1 and h2. So you have all these weights. You have 6 weights here, w1, w2, w3, w4, w5, w6. And you want to find the weights that give you the best predictions possible. So all it is this complex sequence of combining x's together in a very nonlinear fashion to try to get you the best predictions possible. Now, you'll hear people talk about backpropagation. Essentially, you need some sort of scheme to figure out what the weights are. The method of least squares is used for regression. There's an iterative scheme used for logistic regression. There's, again, an iterative scheme used for ridge and lasso type regression models. And there are iterative schemes because you want to find the W's that minimize. So you have some sort of criterion function that we always do. So somehow you may want to look at yi minus yi hat squared. And there's several criterion functions you can use for neural networks. And you want to iteratively go through W's. You start randomly at some place. You iteratively go through some W's. And the method's called backpropagation to find the optimal W's. At the end of the day, you don't even want to look at the W's. You just want to look at, hey, what are my predictions? But again, it's just combining the X's in this highly nonlinear way to get you predictions. Well, let's go through an example to show you how this is actually done in R. And we're going to look at a classification problem. And we're going to try to see whether or not a company pays a dividend. So whether a stock is paying a dividend, yes or no. And we have a bunch of data, not a lot of data, but we have a small data set on whether or not a company pays a dividend, and then we have all these accounting measures of the company, the free cash flow, earnings growth, debt to equity, market capitalization of stock, current ratio, current assets over current liabilities. These are explanatory variables. These are the X's. And the Y is going to be 0, 1, whether it pays a dividend or not. You're trying to identify companies that pay dividends versus companies that don't pay dividends. Well, one of the most important procedures you do in neural networks is you want to normalize the data. You want everything to be on the same scale. You don't want one variable to be a lot larger than another variable in here. And so we normalize the data, and there are several ways to normalize the data. You could z-score the data. A popular way of normalizing it in the literature is do a max-min. And essentially, you just take the range, the max minus min, divide that out, and you can normalize your data set that way. It's called max-min normalization. And here we're reading in our data, and we're applying this normalize command to everything in the data. So every column in the data, we're going to do this max-min normalization to. We're now going to take 80% of our data for training and 20% for testing. And all we're here is randomly grabbing 80% of our rows. And training set is going to get these 80% randomly grabbed rows, and the test set is what's left over. So the minus sign says, give me what's left over after you grab the 80% testing rows. And now we're going to fit the neural network, and this is all you do. So the neural net library in R, and then you say neural net, and then use the same modeling notation we're used to. So we want to model y as a function of these x's, x1 plus x2, so on and so forth. The data is our training data. We're going to do just one hidden node. We're just doing a simple example here, nothing fancy. Linear output equals false says give me probabilities. So it's going to give me probabilities, much like logistic regression does. If we're going to do a regression model, if our y is like a continuous output, then we'd say output equals true, and we'd have y's. And this is what you're seeing, the one hidden node here. It's taking our x's, it's combining them together, going to the interior node, combining, and then giving us an output here. And this is an iterative technique. This says it took 774 steps before our estimates converged, before we got to values that didn't vary too much per iteration. And now we do predictions. So there's a command in the neural net package called compute, and it takes the neural net and your test data. -1 is saying remove the y, because we don't want to have the y in here. Our test set has the y value. Normally you wouldn't even have the y value, so we remove the y. And this is what it looks like, just if you're wondering what the results look like. These are the predictions. And what are these? These are our predicted probabilities. Now it's the classification issue. And so how are you going to classify things? And we're just going to classify things where we're going to say if the predicted probability, this is very straightforward, very simple. If the predicted probability is bigger than 0.5, we're going to call you a 1. If you're less than 0.5, we're going to call you a 0. Nothing fancy, and you can do fancier stuff. We just want to show you the basic idea of logistic regression. So all we're doing here is, look, we're taking a table, and this is the actual value over here, and this is the predicted value. And this is round. So the round is, again, if you're bigger than or equal to 0.5, you're going to round to 1. Otherwise, you're just going to be 0. And you can see, whoa, we're correct 36 out of 40 times. So that's about, let's see, divide top and bottom by 4. That's going to be 9 over 10. That's 90% accuracy. Very simple model, 90% accuracy. That's a neural net in a nutshell. And you can play with the number of hidden nodes you did. We only used one hidden node. You could play with your rule for assigning ones or zeros. Here we just said if it's above 0.5, you're 1. Below 0.5, you're 0. Very straightforward. But that's neural nets in a nutshell. Now, natural question would be, how does it compare with logistic regression? So let's do logistic regression. That's the GLM command here. Same model, we're doing logistic regression. And we're doing it on a training data set. Now, what we're going to do is we're doing stepwise here. So we're doing stepwise regression just to quickly figure out which variables we need in the model. But common thing to do. We're doing stepwise regression. And then we're doing prediction based on our stepwise regression fit. And we do the same table here. And what's interesting, Oh, this is correct. 36 out of 40 times. Excuse me. Sorry about that. And that again is a 90% accuracy rate. Slightly different table, same accuracy rate. And so you're thinking, what do we get? Now, this is a very small example. This is a baby example, maybe 70 rows of data total, not a huge example. But neural networks gave me the same as logistic. So why do I use neural networks? Well, that was a very simple neural network. I got to point that out. Very simple neural network. But why do we use neural nets? Mathematically, it can be shown that a neural net with one interior node, I should say, with one interior node, is essentially equivalent to running a logistic regression. So if you have one interior node, you're equivalent to running logistic regression. More interior nodes, you're better. Now, all this is in theory and in principle. In practice, a neural network model for binary classification can be worse than the logistic regression model because neural networks are more difficult to train. Their iteration, you got to give it data, you got to train it. They're more prone to overfitting than logistic regression. However, the bottom line is that when doing binary classification, you have a 0-1 response. Using a neural network is better in most cases than using logistic regression. And if you're careful and you have a lot of training data, you should be able to get better results with a neural network than you would with logistic regression. Now, we just showed you how to do this with the 0-1. Does the stock pay a dividend, yes or no? You can do exactly the same thing, very similar process if you're doing linear regression. So your y doesn't have to be 0-1. Your y could be a continuous response, and you could do linear regression with neural networks.